Hi students, we are discussing laws of motion. In that different types of forces we are discussing. Okay, so like normal reaction and tension in the string. Yesterday I introduced depending upon system wise, that is depending upon the frame of reference. Okay, depending upon frame of reference, that is there are two types of frame of references, inertial frame and non-inertial frame. In non-inertial frame is one which is accelerating. So the experiments are conducted on accelerating platforms like a trolley, moving train, like that. So if you conduct any experiments on such a devices, such a vehicles like a trolley and moving trains, they are accelerating. If you conduct any experiments, that is while you are determining the displacement, velocity, accelerations and the force acting on the object, such that you have to consider pseudo forces also. In that I gave examples yesterday, few examples. In today's class I am going to explain some more examples. Okay, so that is apparent weight of a person. Okay, so that is apparent weight of a person. The next application is apparent weight. Apparent weight of a person, that is when a person standing on a weighing machine, let it be a weighing machine, okay, what it shows weight of the person. Suppose a person standing on this weighing machine, okay, so it shows the true reading of the person. So if m is mass of the person, its weight mg acts vertically downwards. This person exerts certain force on the weighing machine. That weighing machine in turns it applies a force on the person vertically up according to Newton's third law. That is normal reaction. Okay, so when this weighing machine is kept on the floor. Okay, so if it is kept on the floor, then these two are equal because the person is at rest. It is so the weight shown by this weighing machine is mg. N is equal to mg in this case. So the weight of the person in this case is equal to n, that is equal to mg. It is called true weight of the person. It is called true weight of the person. True weight of the person, that is equal to mg. So true weight of the person, that is equal to mg. Now this is the case 1. Okay, when this weighing machine is kept on a horizontal floor generally. Suppose this weighing machine is placed on a lift. Okay, so case 2. Now this weighing machine is kept on a floor of a lift. What is this? Floor of a lift. It is placed on the ground. Let it be, it is placed on the floor of the lift, that is at rest. So when this floor of the lift it is placed, let it be a lift. Okay, so that is the lift. Now this person standing on this weighing machine. Okay, now this lift is at rest. Then the weight shown by this weighing machine is equal to weight of the person. It will show true reading. Okay, so there is no difference if it is placed on this ground under the floor of the lift. Here case 1, I assumed that this lift is at rest. Okay, so the case 1 is a person standing standing on a weighing machine. Weighing machine. Which is placed on a floor of a lift. Which is placed on the floor of the lift. Floor of the lift. Which is placed on the floor of the lift. Now, case 1. Case 1. If lift is at rest or moves with uniform velocity, that means its acceleration is 0. Okay? Lift is at rest or moves with uniform velocity. So, what happens? So, the weight of the person is equal to, so weight of the person is equal to true weight. So, the reading shown by this weighing machine is true weight of the person. True weight, that is, this weight of the person, it is shown by the weighing machine reading n. So that n is equal to mg. Okay, you call it as equation 1. So this is the case 1. What is the case 1? The lift is at rest or moves with the uniform velocity. Then weight of the person shown by this weighing machine is equal to true weight of the person. Okay, suppose he weighs 50 kgs, then it will show 50 kgs. There is no difference. Now, suppose if the lift is case 2, if lift is accelerating up, lift has uniform acceleration up, lift is accelerating up. Okay, accelerating up with a, what is a? Uniform acceleration. Okay, let it be a. Now, what are the forces acting on this person? Now, see, I will take this one. Okay, so let us assume this is the case 2. Okay, so suppose this is the floor of the lift and it is accelerating up with acceleration a. Now, what are the forces acting on this person? So, the first person is, so since the person is in non-inertial frame, that is accelerating frame, the pseudo force acts on the person. Along with the real forces, you have to consider pseudo force also. So, in non-inertial frame, that pseudo force acts opposite to the direction of acceleration of the inertial frame. This frame of reference, that is lift, accelerating up. So, the pseudo force acts down on the person. So, that pseudo force acts down on the person. What is the magnitude of pseudo force? Ma. Magnitude of the pseudo force is Ma. Now, with respect to person, with respect to lift, the person is at rest, isn't it? With respect to lift, the person is at rest. So, the forces, net forces acting on the person is 0. So, N balances with mg plus ma. So, N now becomes mg plus ma. So, now this N is called N dash. I will write it as N1. Okay? N1. Now, this N dash this n dash. Now the second case, so this is the case 2 diagram. Okay, this is the case 2 diagram. Okay, now this n is called, so this n is m of g plus a. We can also write like this. Okay, n is equal to, now this reading shown by this weighing machine is called apparent weight. So this reading shown by the weighing machine is called apparent weight. So apparent weight n is equal to, we have to write mg plus ma, or m of g plus a. Okay, now the reading shows by this weighing machine increases. Weighing machine increases. Suppose its weight is 50 kgs, now it shows it may be 75 kgs. That depending upon acceleration, or it may be shows more than 50 kgs, or like 60 and 70 kgs, like that. Okay, so it's weight, but that is not the true weight. It appears to be increases because of he is in non-inertial frame. Okay, so that apparent weight of the person increases. That means the reading showing this weighing machine is more than the true weight of the person. Okay, the same argument we can also explain with the help of inertial frame also. Suppose the same thing is situated by a person. He is standing on the ground. He is observing this person. This person is on the ground. He is observing this situation, this event, this experiment. What is this experiment? What is this event? A person moving on the lift, elevator that is rising up with an acceleration a. With respect to this person, there is no pseudo force. So, what is the resultant force here? What are the real forces acting on the person? N and mg are the real forces. In this case, there is no pseudo force, ma, in case of inertial frame. But this person is accelerating up with respect to this person. So the resultant force acting on the person is equal to n minus mg. That is equal to ma. So I will write here. So with respect to, this is I argued with respect to a person on the ground. With respect to the person on the ground, that is inertial frame of reference. With respect to the person on the ground, he is accelerating up with an acceleration a. So I am applying Newton's second law. So I am applying, see I have draw the FBD, n and mg. Okay, these are the forces acting on the person. I assumed that person as a point mass. Okay, and it is accelerating up with an acceleration a. Okay, so what is this? N resultant force should be up with an acceleration a. So n minus mg is equal to ma. That is, I am using F is equal to n minus mg. So what is n? mg, this is ma. Sorry, ma. So mg plus ma. So you will get the same result. Okay. So thus we can argue this instant in two ways. In non-inertial frame, we can argue like this, non-inertial frame, and we can argue the same thing with respect to a person on the ground. We can get here. I am not consider any pseudo forces. Here, inertial frame, you have to consider pseudo forces. That is the difference. This is called the principle of equivalence. So if you conduct the experiments in non-inertial frame or inertial frame, you will get the same result. This is called the principle of equivalence. Okay. Now, this is the first case, case 2. Now, in the next case, case 3. Case 3. Suppose lift is accelerating down. Suppose lift accelerating down. Lift has acceleration down, A. Okay? Then see, we can argue the same thing here. In both ways we can argue, but see, so first I will argue like this. So the lift is accelerating up. This is the floor of the lift. A person standing on this, person is standing on this, it is accelerating down. So here this weight acts always downwards, normal reaction up. Okay, these two are real forces. In non-inertial frame you have to consider pseudo force, that is opposite to the acceleration of inertial frame. Inertial frame acceleration is down and its opposite direction is up, so it is up. So that pseudo force is MA. Since the person is at rest with respect to this lift, so we have, so what we have, N plus MA is equal to mg. So I have N is equal to mg minus MA, that is N is equal to m of g minus A. Okay, so here the apparent weight appears to be decreases, here the apparent weight appears to be increases. Here apparent weight decreases, apparent weight, that is N, reading shown by the weighing machine. Apparent weight decreases. This down arrow indicates decreases. That means if weight of the person is 50 kg, it will show 40 kgs, less than that, less than 50 kgs, because he is in non-inertial frame. That is not true weight of the person. So the reading shown by the weighing machine, when it is accelerating up or down, that is, we can call it as apparent weight. Apparent means not true. Okay. So this is the case 3. Now I will explain case 4. Case 4 is lift is falls freely. That means it has acceleration equal to acceleration due to gravity. Okay, falls freely. That means the lift carries by the threads, strings, isn't it? So this is the lift. Person is standing on the floor of the lift. Okay, this lift carries by the strings. That string has tension. Okay, so what is the tension in the string? When the lift is moving up, the tension in the string is m of g plus a, where m is total mass. That means including weight of the lift and weight of the persons in the lift. So the tension in the string is m of g plus a when it is rising up. Okay, when it is tension in the string is m of g plus a, m of g plus a. What is m here? Total mass. That is lift plus persons. So that is the tension in the string when the lift is accelerating up. When the lift is, see, this is the lift. Lift is moving down with an acceleration a. Okay, case 2. So case 3. So what is the here? Tension in the string m of g minus a. Similarly, we get m of g minus a. What is m here? Total mass. Okay, as we did here. Okay, now suppose in this case if lift falls freely, suppose this is the lift, this thread cuts by mistake. Okay, so then what happens? This lift falls with an acceleration due to gravity. That means the weight of the person. Then what is the weight of the person? So what are the forces acting on the person? Here, when the lift is moving down, what is the tension in the string or normal reaction? N is equal to m of G minus A, isn't it? When it is moving down with an acceleration equal to Ag. So that is, you substitute A is equal to G, m of G minus G. So these two get cancelled. You will get N is equal to 0. That is, apparent weight is 0. Apparent weight is 0 in this case. That means suddenly the string that is carried by this lift breaks suddenly. Then the weight of the person shown by this weighing machine is 0. That means man feels weightlessness. Man feels weightlessness. That you experienced in giant wheels. In giant wheel, that is children's play in a roller. See, in rollers, this giant wheels, children's will play. So the wheels will rotate like this. So when it is moving up, you feel more weight. So, but at the top, when you are falling down from the wheel, what is this giant wheel? From this wheel, giant wheel, when you are falling from top, you are feeling weightlessness. So you can feel that one practically in the giant wheel when it is rolling, when it is falling from top to bottom. Okay, that you feel. So these are the situations, that is apparent weight. Okay, apparent weight shown by the persons in a lift. This is the one of the applications of this. Okay. A man of mass, we take this example. A man of mass 70 kg stands on a weighing scale. Stands on a weighing scale. Weighing scale in a lift. Which is moving, A. First one, upwards with uniform speed. Upwards with uniform speed, uniform velocity. Uniform speed or velocity 10 meter second inverse. B. Down with uniform acceleration 5. Down with uniform acceleration 5 meter second to the power minus 2. C. Moving down with uniform acceleration, upwards with uniform acceleration, upwards with uniform acceleration 5. Next, D. What would be the reading of the lift? So what would be the reading of the lift? Reading of the lift if mechanism failed. If mechanism failed. Okay, and it is hurtled down, falls under gravity. Okay, and it hurtled down freely under gravity. Freely under gravity. Okay, this is very simple problem. As I discussed earlier, you can do this one very easily. So solution, as I discussed in this earlier case, the first case, when the lift is moving up with a uniform acceleration, so for the first case answer is when the lift has moving 8, apparent weight is equal to, for the case A, apparent weight is equal to true weight, that is mg. What is that? M is 70 into g, let it be 10, so that is 700 newtons, let it be. Okay, so the reading of the weighing machine show 700 newtons or 70 kg weight. This can also be written as 70 kg weight. So kg weight is a practical unit of force, that is gravitational unit. If you want to convert into SI unit, newtons, you have to multiply with the g. What is g value? 10. So I will take it as 10. Then it is 700 newtons. This is the SI unit, this is the practical unit, kg weight. Now, so B. So it is moving down with uniform acceleration. So apparent weight is equal to, when it is moving down, apparent weight N is equal to, we have moving down mg minus A. Okay, g minus A. That is, M is 70 kgs, G is 10, A is 5. So that is 7 into 5, 70 into 5, that is 35, 350 newtons or 35 kg weight. Okay, so when the lift is moving down with an acceleration 5, the reading shown by the weighing machine is 35 kg weight. Actual weight is 70 kg weight. Okay, actual weight is 70 kg weight, and actual weight is 70 kg weight, and it shows only 35 kgs. Okay, C. When it is moving upwards, so apparent weight is equal to, so when it is moving up, apparent weight N is equal to, we have M of G plus A, isn't it? 70 into 10 plus 5. So 10 plus 5, 15. So 17 into 15. So how much this one? 7 into 5. 35. 7 ones are 7. It is 105. So 7 into 15, 105. So 1050, 105 into newtons or 105 kg weight. Okay, It is 105 kg weight. Actual weight is 70 kgs. Actual weight is 70 kgs. It will shows actual weight is 70 kgs. It will shows 105 kgs. See, you see the difference. That is called apparent weight. Okay, it is not true weight. Next, D. So when the lift falls, what would be the reading of the lift if the mechanism failed? So if the mechanism failed, the acceleration becomes G. So the apparent weight is equal to 0. So apparent weight of the person is 0. This is the answer for fourth question, D. Okay, that means man feels weightlessness. Okay, take this. So in the same problem, if you want a percentage changes, percentage change, suppose you want the percentage changes, how do you calculate? Change by original into 100. Change by original weight, true weight into 100. So you will get percentage changes. Okay, so the percentage change weight is equal to change. What is the change here? Whether it is moving up or down, the change is MA, isn't it? If it has acceleration A, because true weight is mg, here it is mg plus MA, here is mg minus MA. So what is the change? It is MA increases, in this case MA decreases. So change is MA by original is mg into 100. So that is mm get cancelled, A by Z into 100. Okay, this is percentage change in weight of the person. That is 5 by 10 into 100. That is 1 by 2. That is 50%. So this percentage changes is what we have got. It is 50%. If acceleration is same in both cases, whether it is moving up and down, it is 50% change will occur. Okay, so you observe here 70, half of that is 35, 50% decreases. 70, 50% added, that is 35 added, it will become 105 kgs. So it appears to be 50% more when it is rising up. When it is moving down, it 50% appears to be decreases. The percentage change in the weight can be calculated by using this formula. Okay, percentage change in the weight of percentage change in weight change in weight by original weight into 100. That is the formula. Okay. Now you take another example. Okay, a monkey of mass 40 kg, monkey of mass 40 kg climbs on a rope, which can stand a maximum tension of 600 newtons, in which of the following cases following cases will the rope break? Will rope break? Cases will the rope breaks? Okay. The monkey. So here different cases are given. Okay. Case A, climbs up with an acceleration of 6 meters second to the power minus 2. B, climbs down with an acceleration of 4 meters second to the power minus 2. C, climbs up with uniform speed. Uniform speed of 5 meters second to the power minus 2. Minus 1. Sorry. Speed. D, falls down the rope nearly freely under gravity. Okay, that means moving down with an acceleration equal to acceleration due to gravity. Ignore mass of the rope. Okay, so this is the question. How do you answer this? Okay, so the first one, solution. Okay, I will write here solution. So there is a monkey. See, I will draw here diagram. Okay, monkey of mass 40 kg climbs up a rope which can stand a maximum tension 600 newtons. Let it be this is a rope. Okay, a monkey. See, let it be a monkey. Okay, what is mass of the monkey? 40 kgs. Okay, which is when this monkey climbing the rope with an acceleration, tension in the string will changes. Okay, case 1, if it is moving up with an acceleration A, case A, then the tension in the string is m of g plus a, isn't it? So as I discussed earlier, when the rope climbs up with an acceleration A, tension in the string becomes m into g plus a. So what is m? 40 kg. What is g? Let it be 10. What is a? Let it be 6. So what is this? 16 into 4. What is 16 into 4? 64. Okay, 64. So this is 40 into 16, 10 plus 6, 16. So that is 16 into 4, 64, 640 newtons. 640 newtons. But this it will climb, if you take g value 9.8, still it will be greater than 600, isn't it? I will check that value. Okay, So it is, if you take 9.8 exact value, if you use this one exact value 9.8, so 9.8 plus 6, you will get 15.8. so here 15.8 into 40, so you will get 632 newtons. So 632 newtons you will get when, if you take G value, 9.8, okay, still it is greater than 600, okay. So definitely the string will breaks, because this string, it has its own capacity, can withstand up to certain weight only. If it exceeds, that's greater than that weight, that depends upon breaking strength of the string. That breaking strength of the string depends upon its nature. Okay, some strings will break easily, some strings will be can withstand more weight, isn't it? That depends upon its nature. If it exceeds more than 600 newtons, the string will break. So in this case, in which of the following cases the rope will breaks? For that question, answer is case A, definitely the string will breaks. So case A, in case A, string, that is rope, the rope will breaks, definitely, because in case A, rope will breaks because 632 tension in the string greater than 600 newtons. That is maximum breaking strength of this tension. That is the reason. Now in the second case, if the lift is moving down, the monkey is climbing down with an acceleration 4a. So the case B, what is the answer? The tension in the string is m of g minus a, isn't it? So that is m is 40 into g, let it be 10, a is, let it be 4. So this is nearly 6. So 40 into 10 minus 4 is 6. So 40 into 6 is 240 newtons. 240 newtons. So it is less than 600. So it won't break. So case B, in case B, string, that is rope, will not break. Because tension in the string is less than 600 newtons. That is the reason. Okay, that is the B. Okay, now C, it is climbing up with uniform speed. If it is climbing up with uniform speed, what is the tension in the string? I will write here. So case C, so climbing with uniform speed, tension in the string is mg only. Tension in the string is mg only. What is m? 40 into g, 10. That is 400 newtons. So it won't break because it is less than 600. In this case also, string will not break because tension is less than 600. So next D, if it falls nearly under gravity, so what is the apparent tension in the string is 0. Apparent weight tension in the string is 0. If this monkey falls down the rope nearly equal to acceleration due to gravity, then the tension in the string becomes 0 because the string becomes loose. So when the string becomes loose, there will be no tension because here mass of the string is neglected. Okay, if the string has mass, then there will be tension in the string. Okay, remember this point. If the string has mass, then the tension in the string changes from point to point. If the string has no mass, then the tension in the string will become 0. Clear? Take this. So except in only one case, the string will breaks. In all the remaining cases, string it won't breaks. Okay? Take this. Okay, you take another sum. A pendulum of mass m, hangs from a support fixed to a trolley. The direction of the string theta, when the trolley up a plane of inclination alpha with acceleration a, okay, is first option 0, second option tan inverse alpha, third one tan inverse a plus g sin alpha, a plus g sin alpha by g cos alpha. Fourth one tan inverse a by c. So these are the options we have. So here the diagram is given. There is a inclined plane, okay, that is the inclined plane of angle of inclination alpha. Okay, a trolley is rising up. So this is a trolley. Okay, on the trolley there is a fixed support. Okay, so to that support a pendulum is suspended. Okay, what is this? Pendulum of bob of mass m. Okay, now it is rising up. So a pendulum of mass m hangs from a fixed support. This is a fixed support to a trolley. So that is support is carried by this trolley. The direction of string angle theta when the trolley ups the plane of inclination alpha with an acceleration a. So it is vertical. So the string makes an angle theta with vertical when it is rising up. Okay, so we want this angle theta. How do you solve this problem? Okay, clear? So first you analyze the problem. Okay, now this trolley, it is rising up. So what are the forces acting on this bob? Let us you draw the FBD of bob. Okay, so the tension in the string will be there. So I will draw, I will take this vertical normal to this inclined plane, and this I take this one as vertical and this one I take it as a bob. Okay, So which makes an angle theta with the vertical. I take this one as the vertical. Okay, reference. I will draw this diagram once again. This is the support. Okay, support vertical. Okay, this is the support vertical. Normal to this. Okay, I will take this one. This one is the vertical. So this is the pendulum. I will take this one is the pendulum. This is the vertical to this one. Okay. Now, what are the forces acting on this bar? So, the forces when it is rising up with an acceleration a, what are the real forces? Real forces is mg, that is resolved into two components. It is, what is the one of the component, what is down along the string? It is mg sine alpha. It is down acting along the plane, and it is pseudo force will be acts on this bar. Since it is rising up, the pseudo force acts down. How much it will be? ma. So the real forces is mg sine alpha down along the plane, one. Second one is pseudo force ma acts on this, and the third one is this. See, the tension will be in this direction. So if this is theta, this will be balanced with this. So the component of this tension will balances with this weight. So what is this component here? It will becomes if this is alpha, then this will becomes mg cos alpha, isn't it? Mg cos alpha. So this vertical component, this tension component balances with this is the tension and its component theta. So the component of tension will balances with this mg cos alpha. Okay, this is the component of tension. T is the tension in the string, component of tension will balances with the mg cos alpha. Clear? So I want here this theta. Okay, see in this triangle I want theta. So I am applying tan theta is equal to, so from FBD of pendulum mass m, pendulum of mass m, its FBD is, we have tan theta is equal to, since pendulum is at rest, with respect to trolley, okay, it is under equilibrium. So I am equating the forces. Tan alpha is equal to, so from diagram tan theta is equal to, what is tan theta? Opposite side by hypotenuse. So tan theta is, opposite side by adjacent side. So it is equivalent to this. So what is opposite side? The forces acting on this is in this direction ma plus mg sine alpha. So ma plus mg sine alpha by, I am writing the force components. In the direction force is component of tension, that is balanced with the mg cos alpha. M get cancelled. So tan theta is equal to, what you will get? A plus g sine alpha by m get cancelled g cos alpha. Okay, this is the answer. So theta is equal to, what you will get? Tan inverse a plus g sine alpha by g cos alpha. Okay, Clear this one? This is another example. Okay, take this.